Hello everyone and welcome to our 24th lecture, the derivative rules. This doesn't look correct in English, but I'm not English, so who cares? In the previous lecture, we defined the derivatives using limits. That definition works for every function, but it becomes inefficient quickly. Today we learn the rules that come directly from that limit definition, plus we will get our derivatives table that we can always return to. So first with some terminology, because I always forget and I've been blamed by my friend because, for instance, binomial coefficient is n choose k or something, not n over k, but whatever. So, doing this correctly today, this notation reads as the derivative of the function of x with respect to x. So the x part at the end is the variable we will be deriving for, and f of x is replaced with the expression or the function we're working with. Yeah, so that's it for the terminology, I think. So last time, well, in the mini-test, I mentioned how if you have x to some exponent, the derivative will be the second term in that expansion of the sum. So x plus h to some power, the second term in the expansion of the sum, so the one with x to 1 power less than the original function was, is the derivative of the function, since the first term is cancelled out by subtraction and the h in the second is cancelled out in division, everything. This gives us our power rule. So let's see why, okay? So we have this, and I'm gonna take this first term and then I'm gonna break it apart. So this is like binomial expansion or however this is called. So if we solve this for nth exponent, we get x to the power of n plus n times x to the power of n minus 1 times h, etc. And then as the exponents in front of h increase, they decrease in front of x, on x, sorry. So this is the first part. Now we will subtract this part here, which means that this first term disappears, and we're left with everything from second term forward. Now we will divide this formula with h, meaning that in every term we have here, the exponent on h will be reduced by 1. If the exponent changes to 0, then like h to the power of 0 is 1, so it disappears and we get this. Now because we have a limit of h towards 0, all the terms with h will disappear. We'll be left with only this one, which is our derivative. So this is our power rule. You get a derivative of a power function by moving the exponent to be multiplied by the function and then reducing the exponent that stays over x by 1. So like this, move this one in front and then decrease it by 1. Easy. So let's see a few examples to understand it better. Here are the 3 examples. So let's remember, move the exponent, reduce the exponent that remains, that is the result. So in the first example, 5 is moved in front. The exponent is reduced for 1, so 5 minus 1 is 4, and we're left with 5 times x to the power of 4. Easy. For our second problem, we need to find a derivative of 3 times x to the power of 4. So we move the 4 in front of everything, so 4 times 3 times x to some power, and then reduce that power by 1. We're left with 4 times 3 times x to the power of 3, which when solved gives us 12 times x cubed. And this is the answer to our second example. Now for the last, we see that we have a negative exponent, but the rule still applies because it's an exponent nonetheless. We will carry the minus 2 in front and multiply it with the x, and then subtract 1 from the exponent, and since it's a negative number, it will increase, so minus 2 becomes a minus 3, and this is our result, minus 2 times x to the power of minus 3. So just so you know, this can be applied in all these cases. Now there's special cases again, which they are quite logical, but important to be shown so that we can solve them almost automatically when we come across them, which will be quite a lot. First one is when a function is only a constant, or when we derive by a variable that isn't present in the term. So let's say we have a function of x being x squared plus 2. What would the derivative of this be? Let's see the definition first. We see that for the first part, we transform the function by adding h value to the x. So basically in this function, we will add h to the x, which gives us this. Since we subtracted with the normal function, the 2's would cancel out, as you can see that the 2 was not affected by the transformation through h, or using h for the transformation did not change the 2. Meaning that if we subtract the same function, so minus x squared minus 2, the 2's would cancel out, leaving only the binomial, so the square here, as if the function was only comprised out of the x part. This means that when we take a derivative, the terms that don't include the variable will just disappear. This will lead to a fancy other rule later too, but here we see that if we take a derivative of a constant, it will be a 0, since it's cancelled out. So let's say we do have a derivative of some constant labeled c with respect to x, which obviously isn't present in the constant, since x is a variable and c is a constant, meaning unchanging, yada yada yada. By what we just saw, we know that the derivative of a constant is 0. But this also makes sense, since a function of a constant will have no slope. It will be horizontal, and there is no change of y as x changes, since delta y is 0, delta x is whatever it is, 0 divided by something is 0, so the slope is 0. Fun fact, Desmos will draw out the graph of the derivative, so you can write d over dx and in brackets in front of it, so replacing c with brackets and the expression that you want the derivative of. If it's a single value, it will be listed next to it as a result, and if the result will be a function, it will be drawn. It will not be displayed, meaning you'll have to do mixing and matching to try to find it, but if you're testing if you solved it correctly, you just take the result of the derivative, graph it, and then compare it with the graph of like d over dx of the function itself. Don't worry, I think I showed something like this, or you can test it out. Next special case is the derivative of x, where x is just to the power of 1, the result is 1, as the exponent is carried in front and the remaining exponent is reduced by 1, leaving us with 1 times x to the power of 0, which is 1. And this means that the derivative of some values multiplied to x, the result will just be that value. So like this, the derivative of n times x, the result is n. I didn't say a constant or use the c, as I will mention an example at the end of the video where the other value isn't necessarily a constant, so stay tuned if you want to learn it, or at least be familiarized with it. The next special case is the derivative of 1 over x. So one would think you just reduce the exponent in front of x to get 1 over 1, right? Well, no, we already solved an example like this, if you remember, where x was actually given as x to the power of minus 2. So for fractions, we have to rewrite them as x to the negative exponent. So like this. And when we do that, we can use the rule. And this will be our result. What about the derivative of a root? Well, same principle applies. We rewrite it as x to some exponent, and we know, simply put, radicals are just denominators of the exponent, so a square root of x is x to the power of 1/2, meaning we use the rule as normally we would. So we take 1/2 in front of the x, and then reduce it by 1, which leads to the exponent of minus 1/2, giving us the result of 1/2 times x to the power of minus 1/2, which then again we can rewrite as 1 over 2 times square root of x, which is the result, and these are most common special cases which also apply to the rules. But yeah, some value multiplied to the variable with exponent of 1, the negative exponent, and radicals, and a constant. It's nice to remember these, or at least that all of these apply the same way. They're just the same rule in the 4 different directions. Now, before we get to the table of derivatives, it is important to cover the derivatives of trigonometric functions, and for that we must remember certain identities like angle sum formula, which, if you forgot it, it's found in my 18th lecture at timestamp 17 minutes and 50 seconds. So if you want to refresh your knowledge, of course. But here I will show you how to get the derivative of sine of x, and what the results for tangent and cosine are, but if you want, you can do the same process for the other 2 functions to figure out the result by yourself. So, this is the formula for the derivative and how it would look like for sine. So, we just replace the function with this, insert h for the transformation, and that's it. Now we need to use the formula for the double angle, and I basically copied it from my lecture. I will replace this part with this formula, like this. Now we see sine of x in two terms on top. So this is the first, second, and third term. The first and the third term have sine of x in it. So we will factor it out, leaving us with cosine of h minus 1, along with breaking the fraction line so we have two terms as fractions for ease of solving, like so. So we basically factored out sine of x, and we were left with cosine of h plus, minus 1. And then, since fractions work like this, we can just leave the denominator same for both terms and break it apart like so. And we left the second term untouched for now. Now we can, now as we remember from the limit chapter or lecture, we can rewrite a limit of a sum as the sum of limits. So we will find the limit of each term, then add them together to find the derivative. This kind of foreshadows one of the rules, but we'll get to it. So let's rewrite the first one and the second one. And now, because we can also break the limits at multiplication, we can break the first part into limit of sine of x, and then the second one of cosine of h minus 1 divided by h, because, well, this part is technically a constant because the h is the variable in the limit. So this will not change it, it'll just stay as sine of x. And here, basically it's like an expression, equation, where we have two variables and we put one variable on one side and the other variable and the numbers on the other side. So something like this, but we separate it into separate limits because this one does not have the h in it, this one does. Kind of like that, I guess. But yeah, now we know if the function doesn't have the variable that we're solving the limit for it, we can treat it as a constant, so this changes the current result into this. So sine of x being treated as the constant in this example, times the limit that stays the same as before. And we can also do this for the second limit, the one written at the bottom, because cosine of x does not have h in it, so it's treated as a constant in this example. Now let's solve the limits. The second one is the clear one. We see a familiar identity. Limit of sine of some value divided by that value where that value approaches 0. That's a trigonometric limit where the limit of x approaches 0 and the limit is of sine of x over x and that value equals to 1. Well, if you don't, now you do. I do recommend checking that video because I explained it, I think. But yeah, we know this is equal to 1. So 1 times something is something. So the second limit, or the right limit, or however you want to call it, the second limit is more appropriate in this example, is cosine of x. Now we still need to solve the first one so we can add them together. Now, I hope you still remember how to solve limits. And first, obviously, we try to insert the value at which the limit is, so we insert 0 here instead of h. But this limit would give us 0 over 0, but we don't know how to solve it because that requires L'Hopital's rule, which we will learn next time, as it's a use of derivatives, so we will help ourselves with Desmos. This is our graph, so this is the function here, and as we know, cosine of x at x is 0 would have its y value at 1, but basically it would have its highest point at x is 0 for y. But then we transform it and we move it to the left for 1, so that moves the whole point into 0. Basically, cosine reaches the peak at x equals 0, but this one is transformed, moved to the left, so now it doesn't reach it. Now the 0 is at 0, just like a sine would be, but sine usually goes up, so that's a slight difference, who cares? And then we divide it by x to make this point undefined. You can go back to the trigonometric lectures, I'm not gonna explain it a bit longer because I've already explained it. Basically, we use the cosine graph, transform it, move it to the left, and then divide by x to basically delete the point 0, 0 to make it undefined at that point, making it harder to determine the value at it without the limits. But using Desmos, because we don't have L'Hopital's rule, we know that the limit is 0. So this whole part becomes a 0, and what happens when you multiply with 0? You get a 0. And these are the two limits. Now we add these two infinities together to get the result, which basically means that only the second limit is the result alone, because 0 plus something is something. So the limit is cosine of x, and this means the derivative of sine of x is cosine of x. So at any point of the sine function, the slope will be equal to the value that the cosine function has. Well, you can look at the graph and see for yourself. When the function reaches the top or the bottom, the cosine has a value of 0, which is where the biggest slope is, negative and positive. So something like this. So red one is sine. Let's say here at the top, sine is flat. This means that its derivative has to be 0. It is 0. In the middle of the slope is the steepest slope, whether positive or negative. So that's where the cosine peaks, in the positive or negative. So yeah, here are both graphs in the same coordinate system, so you can compare it. And you will see something about the slope of the cosine function and the value of sine, which again you will see on the next slide. The relation, so the derivative of cosine, so the slope of cosine compared to sine, is not the same as the slope of sine compared to cosine, because in fact it's the opposite, or however you call it, because as promised, that was the derivative of sine and how to get it. Here are the derivatives of all three main trigonometric functions listed. We see that the derivative of cosine is negative sine. So whatever the sine of x would be, we change it. And derivative of tangent is the squared result of secant of x. But you won't run into this one as often though. I'll still give you the table later, which, without it of course, I list on the next slide. But if you look at this, so cosine is blue. Its slope here, so it's increasing, so the slope should be positive. The sine value is negative, the negative peak, so the highest negative value. So the absolute value of the sine is as its highest, but the sign in front of the actual value is negative, or the opposite of the one that it should be. So therefore the minus correction. You can do this for yourself and see how this works and why this works. But yeah, no, these are the derivatives. That will be quite common, I think, later on, a lot. Not as much as the power rule, though. But yeah, here is a table of derivatives. You can screenshot it, copy down, or whatever. As you can see, we have our derivative of the constant, exponent, radical. Then we have the two of trigonometric derivatives. And the last four, the two for logarithms, so natural logarithm and logarithm with a different base, and two for the variable in the exponent. We didn't really get the logarithm and the exponent ones solved, unfortunately, but here they are. If you look at the constant to the power of x, you see it's comprised of two factors. One is repeated constant to the power of x, and the other one is the natural logarithm of that constant. While if we replace the constant with e, which is also a constant, a derivative of this function will equal to the function itself, which is a super handy property because, well, it makes sense. Natural logarithm of e is 1, because natural logarithm is basically just logarithm with base of e. So to what power must you raise e to get e? 1. Easy. So yeah, these are very helpful. More often than not, you're gonna be running into the derivatives like this one, these two, and then logarithms. Sometimes e to the power of x. It will actually be a modified x, but we'll get to that in physics. Don't worry about it. So yeah, if we ever need derivatives, I will either use it from this table. But if the example is really extreme, I'll give you the derivative formula to you on the slide. So usually you use the tables and rules instead of the formula we learned last time. So now that we have covered the common derivatives, let's learn the rules to even know how to solve harder derivatives. So the first one is the sum and difference rules, and they aren't really a big thing. Well, they are, but they aren't, since the derivative of a sum is a sum of derivatives, same for difference. I mention it just in case someone doesn't know, but as I did, the rules are almost the same as for limits. If you're confused on the notations, don't worry. On the next rule, I'll explain what u and v is and what everything, how to determine each part, etc. But basically, to find the derivative of a sum, you sum up the derivatives of individual parts. Now for the product rule, which is the first actual rule that we have to do something, because this one has a formula for it, you will see that these rules are basically the same as those for limits, as I said before, and it makes sense since derivatives are basically limits. But they make the solving so much easier than just using, just by using these rules in tables than if you were using the limits formula. So let's say you have a function which is a product of two functions of x. One example would be 2x squared, since we could rewrite it as 2x times x. So it's easier to set generalized rules that you can use on almost any example. If you just find a way to rewrite the function as a product, sum, quotient, or whatever, you can use the appropriate rule. So a derivative of such a function would be written as the derivative of u times v plus u times the derivative of v. Of course, this is u of x, v of x, derivative of u of x, derivative of v of x. I'm just shortening it so it's easier to remember, because if I have everything with brackets and everything, it gets confusing fast. So, long story short, you find a way to break the function into a product of two functions, get both their individual derivatives, and insert them into the formula like this. Yeah, basically this. In this case, the order doesn't really matter because it's multiplication. And you basically just add them together. So yeah, in the quotient rule, so the next one, it will be important, so try to remember how and why. But onto the example. There's plenty of ways to break it down, but our goal is to find two functions that we know the derivatives of. I will solve this in two ways. First, to demonstrate the rule, so with only two factors, and after this I will expand on how to use it if you have multiple functions, like 3, because this one technically could be broken into 3 functions. So I wrote out what I will use as the u and v functions, and then I wrote their derivatives, which I got from the table. So the u of x will be x squared, and v of x will be sine of x. If I take the derivative of u of x, I get 2x, and if I take the derivative of v of x, I get cosine of x. These are the prerequisites to use the formula. It's good to know them. So I set the formula, and I just insert the values. So u prime, unfortunately the prime is bent to the right, so it looks like it's on the v, but it's actually on u. So u prime is 2x, v is sine of x. And then u is x squared, and v prime is cosine of x, which gives us this. Now that we have this, there's nothing more to be simplified. We could factor out x or whatnot, but this is our result. You can check in decimals by writing d over dx of x squared times sine of x, and then a second function being the result here, and you will see the overlap. Now, to solve it as 3 functions, I will take our formula and expand it, so I will treat our u of x as r of x times k of x. So basically, this is the normal formula for the function, which is built from 2 functions, and now I wrote it as the function built from 3 functions, if this kind of makes sense. Now, I set the r of x and k of x functions, so what they will stand in my example. Now, since there is a u prime factor, so the derivative of u, we also need to find that derivative of u using this rule, because we can't just assume it's a harder function, like they're not just x's, they could be x and sine, so it would be x times sine squared of x or something like this. So basically I will use the same formula here for u function, because the u function is technically comprised of r of x and k of x. So let's replace this f of x with u, and then this u with r, and this v with k. So I hope you see the parallel here. So I use the same product rule on the u of x function, so this slot here, and that gives us the derivative of r times k plus the r times derivative of k. Now I will insert this all into one formula, so it's easier to see how the formulas change. So I colored the derivative of u with purple, and all of these components. And I color the normal u with orange because I'll insert this in, assuming, like, because u of x no longer exists for us because we have three functions technically, and u of x was just like a function made out of two. So basically I'm inserting the derivative and the u value, and we get this formula. So the derivative of r of x times k plus r times derivative of k of x altogether times v, so sine of x, plus r times k, so r of x times k of x, times the derivative of v of x. So we're basically just inserting different functions or different rules. So it's working with multiple equations. So you cannot forget that lecture because that one is very important as promised in physics and even in math. Who would have thought? So yeah, you just find different relations between different functions, variables, and put them into one formula. And now that we have this done, I will insert the derivative of this is 1 and the derivative of this is 1, so I write it on the right. I copied the formula to the top so it's easier to work with it. And then I insert the values. So here, yes, derivative of r is 1, k is x. R is x, derivative of k is 1. So we get this in the bracket. V is sine of x, which for some reason got colored purple. That's my fault. Plus r times k is x times x, times derivative of v is cosine of x, gives us this. Now 1x plus 1x is 2x, so we get 2x sine of x plus x squared times cosine of x, and this is our result. We see it's the same as before. I hope this was a clear example on how to use the rules in case you have or ever have more than two functions, and it's to just combine the functions and keep the labeling consistent. Because if you're consistent in labeling, you can pretty much solve almost any problem, as long as it doesn't require any complex formulas, but then again, we can make them up with derivatives and stuff. Now, next property is the quotient rule, and as the name suggests, it's a rule for quotients or division, and is as follows. For a function that can be written as u of x divided by v of x, its derivative is obtained by following this formula. And that's similar to the before, but now with a difference. Derivative of the numerator, so top, times denominator, minus numerator times the derivative of denominator, divided by the square of the denominator. So in short and simple, derivative of top times bottom, minus top times derivative of bottom, all divided by bottom squared. But since we know it's easier to see an example, let's go solve one. We have our cosine of x divided by x, and now we need its derivative, so let's get our formula. This is the general formula. Now I write out the u of x, so the top, and the v of x, the bottom. Take the derivatives. Be careful because cosine of x, its derivative is minus sine of x. And now I will color code it all because we love colors. So u is purple, derivative of v is green, v is blue, and derivative of u is orange. So this one is here, and I just insert them in so it's easier to follow, because you don't see me write because I only scroll ahead the pre-made scenes, which is one of the downsides of this online setup, and which is why physical or IRL school can benefit so much more if you just give them a chance. Well, that and good teachers. So yeah, basically I insert these values as the color-coded are, and I get this. And then I factor out the minus sign because I'm lazy as fuck. So minus goes out, we have this plus that, and this is our result. I know it doesn't look simple or pretty, but that's just how math is sometimes. But it is also quite simple at this stage, of course. But yeah, this is the example for quotient rule. Now for the next one, this one is new, but it will make sense why we need it soon. So by now, with all the results, the rules, and the table we have learned, we can solve the derivatives of sums or differences of functions, the derivatives of products or fractions. But what if our function is something like this? How would you even call it? How would you try to simplify it? Well, this is called a composite function, and it's a function inside another function, so one is nested inside the other. Well, how do we find its derivative? Let's see. You will write it out as some g of h of x. So instead of x in g function, we have another function of x inserted as x. So back to the example, we inserted x squared inside of x inside of the sign. Kind of like that. In a way, every function is a composite function of the function itself and a linear function, so x to the power of 1, as the one nested inside the outside function. So this rule must account for that in a way that when using it on any function whatsoever, it would give the same answer. So either that the linear function doesn't affect the result, or that it affects the result in a way that we can predict with any other rule. Well, it turns out it's this. So the derivative of our composite function is equal to the derivative of the outer function, where we treated it as if it was a normal function. So for instance, sine of x squared, we would take the derivative of sine as if it was like a sine of x, but we would get cosine of x. Actually, better example, we replace x squared with like an a, and then we take the derivative of like d over dA of sine of a. And then after that's done, we get cosine of a, and then replace back the x squared instead of the a to get the cosine of x squared, for instance. So we would take the derivative of the other function and then leave the x squared or the second function inside it untouched. But don't worry, you'll see it on the example in a bit because this might sound confusing. And that inserted function still has a role to play. So we take its derivative individually and multiply it to the derivative of the outer function. Sounds complex? Well, it isn't really. The formula is simple. After you use it a few times, you also pick it up fast and it doesn't cause any more problems. So really, trust me, once you use formulas a certain number of times, they become muscle memory. Like, if you want to be good at math, solve problems. I know this is ironic coming from me, who barely ever solved any problems for math, and I just nerded out the formulas and hoped for the best. But from personal experience, solving problems actually works. So let's solve our example, sine of x squared. Now I will write out what each part is. So we have our function, we have the formula. So on the left, there are the functions, so the outer function g of x and the inner function h of x. And then on the right, there are their derivatives. So the derivative of g of x would be cosine of x, and the derivative of h of x would be 2x. So let's color code them, because yay colors. I have color coded all the parts that are important. As you can see, the derivative of g has a differently colored insert. That's because we need to make sure that we have inserted the original function, into the derived outer function. So whatever the derivative of g is, we replace the x in it with the h function. So let's fill it in, right? I should do this step by step. Now in hindsight, this makes more sense. So first I'd write the cosine of h of x, but let's just insert everything as colored, and we get our result. This is it. Hopefully you now see that this isn't as hard. If it still is, I have one more example for you, which we can solve two different ways. We could solve it either by breaking down the exponent following the Pascal's triangle, or do it by hand if we so want, but that takes time. So this rule saves us in that regard. And let's see how. The outer function that I marked as g of x is x to the power of 5. So this entire bracket is treated as x, and this is the exponent. Its derivative following the power rule is 5 times x to the power of 4, while the inner function is 3x squared plus 1, and its derivative is 3 times 2 times x, which is 6x. And the plus 1 disappears as it didn't have a variable we were deriving with. Now we write out the formula and insert the values. This is the formula. I color code it again like before. I insert the red into red, purple into the purple, blue into the blue. And we get this. Now, of course, we can reorder this around and make it look prettier, like multiplying the 5 and the 6 together, because this is all multiplication. And this gets us our final result. Simple, right? Like, it's not that complicated. Just solve a couple of examples and Trust me, you will know this. You will be a master. Now, as promised before, here I will introduce partial derivatives, but I won't really teach them since this falls under more advanced stuff. If you want me to make a video on them, comment down below, and if enough of you actually want it, I will come back and make it. But I will show you an example and partially solve it. So we are familiar with functions of one variable. But if you think back to when I introduced coordinate systems, there was an example where I showed a 3D coordinate system. It involved x, y, and z, where the function is usually written as a function of two variables. So this is the function we know, and this is the function that I showed then. So something like this. But how do derivatives work for such functions, since remember the derivatives can be marked as d over dx, and there's like only one variable underneath. So something like this. This would mean the derivative of the function that we know consists of x. And if the function doesn't have an x, for instance, if it was a function of y, so something like this, there is no variable x, so the one that we are taking the derivative with respect to, the entire function is treated as a constant, so the derivative will be 0. It makes sense since we're looking at the slope in the plane of x coordinate and the result of the function coordinate, so x and y, and in that changed coordinate system, the function that doesn't have x in it would be constant. So this is all complicated, so you don't have to pay attention if you don't want. This is just me nerding out. So here is a 3D graph of a function of y. We see that it's a linear function, so a function of y that equals z. So just like this one, f of x equals y, it's a linear function in the second and third dimension, kind of. So we're observing the change of z as y changes. If we take the derivative with respect to x, we're only looking at the xy plane, so where the z value is 0. So I will edit this formula with the condition. This is a condition, so I'm only looking at the slab, a cut of this, where the z equals 0. So we can actually look at the appropriate value, because, well, there is no z present in the d over dx times y. I think I forgot how. Oh my god, I'm overcomplicating this so much. Basically, so I define it as z equals 0, since that's the value of z in a x, y, 2D coordinate system. And now our derivative is the derivative of the function. Also, basically, the cutout of this is a function, and we're looking at its behavior in a certain position. This is this position, and if we want the slope in that position, depends on the variable, of course. In this case, the x variable. But we see it's kind of diagonal, so it's gonna be hard to look. But imagine this is the y up, and this is the x right. We see that it's a constant, so the y doesn't change as the x changes, meaning its derivative will be 0. So yes, if the variable with the respect to which we're taking the derivative isn't present, so bottom one, the function can be treated as a constant, even though we can all see that it's linearly increasing, right? But along the x-axis it doesn't change. Regardless of which part you look at, along the x-axis is constant. Well, of course you have to look at the y and x, because, well, I think the z of x... Yeah, if you look at the z of x, it's just everything is red, so it doesn't kind of show the perspective really nicely. But yeah, now that I have overcomplicated this law far too much, let's see on how to actually work with multiple variables. So let's take our function of x and y, which equals z, and the function is x squared times y plus 3xy squared. What would our derivative be? Well, there isn't one. Well, that's not really right, but also not wrong. The truth is there isn't one. There is two, and they are partial, because it's a slope. But for slope, you have a formula of change of one variable divided by the change of its independent variable. In this case, we have two independent variables, meaning we could write two derivatives. That's why they're called partial. This is oversimplification, so don't quote my word for it. It's just a way of explaining so you can understand, but may not be the best explanation. But yeah, because each doesn't represent the whole derivative or slope, but only a part of it. So we write out our formula for slope, but because it's a partial derivative, they have a slight change in symbols. So instead of using normal small d's, we use stylite curve d, also called a partial, a curly d. Basically, just note that there is more than one variable in the function. So, vroom. So if I were to draw it like here, it's like, vroom. That's not really right, but like something like this. This is, I guess, not to be confused with delta, which is something like this. This is also horrible. Ignore this, thank you. But yes, basically this signifies that there's more than just one variable in the formula or the expression, the function, whatever. So I copy this again, so partial over partial x times the expression we have. Now I will color the variable that stays the variable for the sake of solving with orange. Everything else, so colored white, will be treated as a constant. So in the first example, we're deriving with respect to x, so I color x as orange. And in the second example, I color y is orange. The rest is like if it was like a number 2, number 5, number 7, number 98, whatever. And now that it is done, we just solve. And we obviously can use normal rules for solving, so sum rule, product rule, etc. So product rule in the first example, let's say this is 3 times x squared. We take 2 times 3 times x, but that 3 is actually a y, so it's 2 times xy plus 3, this one disappears, y squared, because, well, x is to the power of 1, disappears, so we use the n times x, its derivative is n rule. And in the second example, again, this y is to the power of 1, so it disappears, this one is to the power of 2, so the 2 gets carried over, and it stays as the power of 1. These are our answers, and we write them like this. This is it. Now, thank you so much for tuning in to today's lecture. It's a long one, and there's a lot of stuff going on. But I'm glad that you stuck through with me. Here is the mini test again. Best of luck solving it. If you have any questions, join the Discord down below. I love to help people. Comment down below any questions you want, requests for any videos that I can make out of schedule to help you solve problems, explain certain concepts. Imagine me as your teacher that doesn't bite. Like, any teacher is happy if you ask them a question because it shows that you are paying attention. If they're upset with you, that means that they are either a poor teacher or that you usually like to cause trouble. But I will gladly help whenever and wherever I can. So if you have any questions whatsoever about this, comment down below. It's better to ask and learn, or ask and try, than to not try at all, because you can only win if you try. If you never try, you cannot win. This was it. Thank you so much for tuning in today. I wish you a great rest of the weekend, and I'll see you all on our next quest. Bye!